Exercise 6. Begin by creating a new project. So we'll just click on map there, and we need to locate our work folder. This usually, it's not going to be there. For me, it's going to be under C, users, and then my name, and then I want documents. The other documents was the wrong documents, obviously. It's the one on H colon, and I want this one anyway. So I go to here, so I'm saving it in the right location. This should be H colon for you. You want your name, and then documents. If you've hopefully created a documents folder, the course name there. And then we need to call this exercise 6. No spaces or anything like that, just nice and simple. Exercise 6, create a new folder for this project. Yes. Click on OK, and we should have a new project folder created with all the project files associated with this. So we can actually just get rid of those two and remove those. We go to catalog. If you can't find catalog, it'll be under view. So if you go there, you can find it there, but we're not interested right now. We have catalog pinned to the side here. And we go to folders, and here we can see that we have exercise 6, a folder for it there with its database and a toolbox. But what we don't have is our raw data. So if we right click on folders, add folder connection, and now we need to once again try and locate. So we go to there, please click on there, and then there, and raw data. There we go. Click on that. And that gives us our raw data. That's the start of the project. The next thing to do, while we're at it, let's just read the data in just quickly. So if we go to get there, we have 2 files to read in. To begin with, we can read in our RGB there. Let's pull that in. It's adding data. There's the RGB file, and then we go to there, and then take the IRF file in. That goes there. So we've now read in the 2 files. Let's just quickly save our project and then go back to the instructions and work out what it is we're going to do. So the idea here is that we will do an analysis of the colors in the image. In this first image, which is the aerial photograph, we're going to do something called a normalized difference vegetation index analysis. In the second part of the exercise, we'll be looking at a satellite image from Sentinel-2, and we'll perform a more complicated analysis. So this you may recognize from the lecture. If not, this is the electromagnetic spectrum, part of it at least, from the visible, the ultraviolet, even towards the ultraviolet anyway, blue light, through to the infrared, through the near infrared and the more distant infrared. And these are the bands that the Sentinel-2 sensor can pick up. But we'll use this illustration for our aerial photograph as well. So our aerial photograph is sensitive to blue light, so this part of the electromagnetic spectrum here, to green light there, to red light, and to near infrared. But we've been given 2 images, one containing blue, green and red, and one containing green, red and near infrared. As you can see, the Sentinel-2 is capable of sensing many other parts of the electromagnetic spectrum as well, many other shades of light, colours of light. And this, our aerial photograph, is broadly similar to this. It's not exactly the same, but it's broadly similar. Our eyes don't quite see this, they definitely don't see all this, but there's something along these lines. This reproduces, these 3 here would produce our true colour image, whereas these 3 here, B3, B4, and this B8 there, the green, red and near infrared, give us this image. So what are we going to do with this? Well, we're going to, in the first part, this normalized difference vegetation index, is we're going to utilize the fact that leaves, fresh vegetation, healthy vegetation, strongly reflects near infrared light, but absorbs a lot of red light. It reflects some green. It's quite strongly reflecting in the green in comparison to the blue and the red, but really strongly reflecting in the near infrared. And we're going to use that relationship between the red and the near infrared to look for vegetation in the image. We can't really see anything else. We can see stuff that isn't vegetation, and we can see stuff that is vegetation, but we don't make any decision on what not vegetation is. It's just not vegetation. So this is all that this is good for. It's very good at finding vegetation, not so good at anything else. So that's what we can use it for, and it's a very commonly used tool. It's so commonly used as a built-in tool for it in ArcGIS Pro and in many other applications as well. But the way it works is that we're looking for this relationship between the red and the near infrared, that we have a weakly reflecting signal in the red and a strongly reflecting signal in the near infrared. One question we have to address then is, how strong is that signal? Well, that's going to vary over the landscape, over the image, depending on shade, depending on illumination, the slope of the topography. Lots of things are going to adjust the strength of the total signal coming through, and still our index needs to work, which is why we normalize it. That's what the N stands for, normalizing, and that refers to actually this lower part of our equation here. So in this equation, the top part says take the strength of the infrared signal here and subtract from that the strength of the red signal. So we get a slightly weaker signal. That's good, but what happens if we have overall, if both of these are very weakly reflecting, but the relationship between them is the same, we're in shade somewhere, well, the total strength of that signal is going to be much, much less than, say, in a brightly illuminated area. The relationship in a brightly illuminated area of green leaves will be the same, but the total strength of the signal is going to be much stronger because it's strongly illuminated. Therefore, we use this down here to normalize it. We add the strength of the total strength of them together and then divide this part, the upper part, by that, and that normalizes the signal so that regardless of how strongly illuminated it is, what we get is this relationship, the relative jump from red to near infrared. And where we have a big jump like that, a big strong signal, that means we've got vegetation, or is strongly indicative of vegetation. That's what we're assuming is vegetation. Where it doesn't do this, it's something else. It's not vegetation. So that's what our analysis is going to be. So what we need are, for this analysis, we need two bands. We need the infrared and the red. So we need to find those in this image. So if we return back to here, we've got our near infrared image here with 3 bands of data, and we've got our color image here with 3 bands of data. They look quite different. This is our true color image. Looks pretty much as we would see the world if we were up in an airplane looking down. It's not entirely the same, but almost exactly the same. And then we have this near infrared image, which is quite unfamiliar, perhaps. But here we can see that what was green, very green in this image, in the true color image, is now bright red. And what was green, but not quite as green, quite dark green, the coniferous forest, is this dark red. And then we have black, non-reflecting parts. This is water. It's absorbing most of the light anyway, so we don't get much light reflected back. And then we have this cyan color, where we have dry, low vegetation conditions. So it's both dry and very little vegetation. So the cyan color is indicative of some colors being missing. So work out which colors are not shown. If we go back to the color cube and the cyan, yellow, magenta, contra red, green, blue, and see which colors are missing to create the cyan color from this. And this is a standard color palette for vegetation mapping. But we need to work out, we can see from this which color is which if we know what's going on, if we think about things. But to confirm our suspicions, let's quickly look at the metadata. So if we if we go to the raw data here, and we go into our folder and we want the ortho IRF, here's our TIFF file. But actually, if we go to the metadata here, we can see we've got these 3 JSON files. So JSON is just a JavaScript format for storing data. It's quite commonly used. It's a reasonably flexible format. plain text. Now there are 6 files here, but actually what we have is the image that we're looking at is actually a mosaic of 2 different images put together and then clipped by me for you. And so that was these two images, this group here and that group there. And each image has associated with it in its metadata these 3 JSON files, one called Flygbild, one called orthophoto, and one called uttag. So that's the aerial photograph, this is the ortho-rectified photograph, and this is the extraction from the database. So if we can open up, as these refer to 2 images taken at pretty much the same time, a few seconds between them, from the same data acquisition, we'll just look at these first 3, because it's essentially the same information in these others. We'll open those in a text editor, and here are all 3 files, and this is just plain text. So if we begin with the aerial photograph up here, this Flygbild, and the acquisition date is 2013. The elevation the aeroplane was flying at is 4,800 somethings. We're going to assume meters here. It's slightly annoying that it doesn't actually tell you that it's meters. Maybe that's just being a pedant, but it would be nice if they were actually to specify the units. And here's our time, 2013, May the 16th. And when we look at this, let's just remember that date now, May the 16th. We can see that we've got 4 bands of data in this. 4 bands in our near infrared image. Well, actually, because this is the original image, this is the aerial photograph, the camera that took the image actually took all 4 bands at the same time. So it took red, it took green, it took blue, and it took near infrared. So the acquisition of the data occurred at the same time. This is interesting. Why is this interesting? Because infrared data is used for vegetation mapping. The other 3 can be used for other sorts of mapping, but we really want this near infrared for vegetation mapping. And early spring, late winter image acquisition is good for seeing the ground. For vegetation mapping, we want something later on in the season, once there is actually some vegetation. And for those of you unfamiliar with 60 degrees north in Sweden, which is approximately where we are, mid-May isn't terribly verdant. It's the beginning of spring, we're starting to get some budding and it's starting to green up, but it's actually quite early, really, for our idealized vegetation mapping, or ideal vegetation mapping rather than idealized. But okay, this is what we've got. We're going to have to live with it and just accept that this is the problem we've got. So that's the image that was acquired. We can see that from one image we got all 4 bands, but what's been delivered to us is different. So if we go here, the ortho photo, the ortho rectified image is sort of been laid out flat, as it were, removing deformations due to the camera angle and just the fact that you have a parallax effect, plus the DEM model was used to flatten out the elevation. So we get this ortho rectified image where we have 3 bands. We have in the first band infrared, then red, then green. What we would expect from a near infrared image. Really, we could have just bolted on the end here the blue as well, and we'd have been fine. We would have saved ourselves a lot of space. Instead of having to download 2 images, we could have just had 1 with 4 bands rather than 2 with 3 each, where 2 in each one are repeats. But that's just the way it is. So that's what this one shows us, and we can then see the band order. So band 1 is infrared, band 2 is red, band 3 is green. And then when we look at this, that's then also repeated here. We can see we've got band 1, band 2, band 3. It doesn't tell us explicitly what the frequencies are of these in this, but we're assuming that order there is the same order as there. It's an assumption, and I'm going to say that assumption works when I look at this image, because this looks as expected, whereby the bright red colours are the near infrared coming through in the red band. So we've managed to read in our data, we've managed to work out what is what, and now I think we'll end that video there and move on to the actual analysis in the next video.